So it's my privilege to introduce Kai-Wei. So he joins us from UCLA as an associate professor. He's an extremely accomplished researcher in machine learning, natural language processing, computer vision, lots of great work in multimodal reasoning, as well as a lot of very influential work in exploring the biases that the models have. He's currently an elected officer of SIGDAT. So this would be the thing that the organization that runs EMNLP. In a couple of years, he'll be our president. So that's exciting. For those unaware, SIGDAT was founded by David Jarowski locally here, who's been an active member for a very long time. And so, Kai-Wei, thank you for your service.
Thank you.
Amongst many high papers, one in particular, actually, there's multiple of Kai-Wei's highly cited papers locally to my lab, but say one going back into the 2000s, which has an extreme number of citations for the software package lived linear, which he did as an undergraduate.
Yeah,
As an undergraduate.
Yeah.
Has over 10,000 citations. And back in the many years ago, statistical NLP, the key thing that really stopped us from making forward progress was just how efficient your underlying solver was for doing logistic regression. And so lived linear was just this amazing package that I think enabled just a mammoth amount of work over about a 10-year period that everyone was using this, hence the massive citations. Anyhow, I'm eager to hear what you're going to talk about today. And so please give Kai-Wei some applause.
Yeah. Yeah, thank you, Ben, so much for the introduction. Yeah, I'm very excited to share with you here about our research on how to build in trustworthy AI by teaching machine using language and rules. So as everyone know, as AI now playing more and more increasing important role in our daily life, and we think trustworthiness is one of the most important critical part to allow people to actually use those NLP technique or AI technique into the real applications. So in today's talk, I will first give you a general overview of my research on this trustworthy NLP area. And then I will dive into two lines of the research work to talk about how we can teach a machine using language and rule and guide them to be more trustworthy. Okay, so let's start. So imagine that you meet a new colleague at work in their first day. So if they are competent and they can consistently deliver the work they promise to do, then over time, you will earn trust with them and you trust them and you can work with them on some important task. But now imagine in an upside situation, what if that new colleague cannot really explain how they make decision in a reasonable way. And also they don't spend their effort to understand the culture of the workplace and show care about you, then over time, you will still start to losing trust with that colleague. And at the end of the day, you won't be able to really work with them on some good task. So Dr. Free, a professor in the business school at Harvard, she gave a talk at TED to talk about her experience about how to build and rebuild trust with her experience with Uber in 2018. So she argued trust has three fundamental drive: authenticity, logic, and empathy. So let's take a deeper look of each of these components. So authenticity means that you want the person work with you is be real, be ethical, and you know they were not going to deceive you for their interest. And logic means that you want the person to work with you to show their competence to perform the task, right? And then give you the evidence and the reason behind the decision, so then you can trust they can perform that task well. And emphasis means that you want that person to care about you in a way that it could make a personal connection, and then you know they care about what you are thinking, what you do. So this same principle can be applied not just for human and human interaction, but also for human and machine interaction as well. So in the context of AI, you can thinking about now this authenticity means that you want the model to be safely aligned, and it can be transparent, to be safe, to be fair to all the way it operates. And then users should feel confidence to use this system, and because this AI behave is ethical and aligned with your expectation. And in terms of logic, this is a thing that most people are working on. So you want the model not only can work well in those benchmark data, but can actually be robust when you deploy it to the real world situation, right? It can adapt to the new environments, and when it fail, you know why it is failed, and when it work, you know that what is the reason made the thing work. And finally, emphasis is related to the inclusivity and the cultural awareness, right? So you want the model not just only work for certain people, but also working for everyone. And you can serve all different users with different background, different gender, different language, so on and so forth. So this is kind of thing that drive my research since 2017. So we have been working on a bunch of a direction of how to build trust between human and the machine. So we start looking at the problem of the fairness, and then we move on more and more nowadays to the robustness and the reasoning of those NLP model, and show how they can be more inclusive and then work for different type of tasks. So I have been given various tutorial in the NLP conferences about this topic. And today's talk will be talk about part of this thing that we did over the year. So beside the research work, I also organized this Trustworthy workshop. This is our fifth version of that. So this workshop has been attract a lot of participants' interest. For example, in the ACL one, we got like 800 people say they want to attend this workshop, although it is about like 150 people show at the end. And we're going to have the fifth version of this workshop in NACO this year. And this version, we were going to jointly host a workshop with a private NLP, because that become a very important component of a trustworthy NLP. And we're going to put a call for paper soon. So if you have a word related to that, please submit your paper to our workshop. Okay, so that's back to my talk. So in today's talk, I'm going to focus on arguing how the language and rule can be a powerful tool to guide the LLM to learn trust. So in the first part of the talk, I will use the vision language system as an example to show that how we can teach machine through the language description, and what is the problem and how we solve those problems. And then I will talk about how we can teach the machine with rules and the constraints. So this part is a little bit more technical. And we were going to show you how you can embed those rules in the inference and the training for LLM. And finally, I will talk about a little bit some application I'm interested in to collaborate with people outside the CS departments. Okay, so let's start with the first part. So one of the problems that I would like to show back to 2019 is that how we can teach a model to learn some new visual concept and locate that particular concept. For example, how we can locate these paramedics in this image. So the traditional way to doing this is that you can collect maybe hundreds and thousands of images of the paramedics. And then you ask a model to learn from those images and then to generalize, and then you can make a good prediction. But this is not the way you teach a human to identify the new visual concept, right? So imagine you are teaching a kid or someone to do this task. The way you're doing this will be you provide a description, right? You will say, well, recognize the paramedics, and it will be the person usually wearing some uniform, has a patch in their or logo, right, in their shoulder. And then they usually wearing some light color jacket, and they usually have some equipment, glove, goggle, this or that. And then use that contextual information to teach the human to do this recognition. So then the question here is, can we do this thing to the machine also in the inference time? Like I give you this kind of description on your right-hand side, and then that model just read this description and to recognize that particular objects that you mentioned. Okay. Okay, so that kind of a start or journey since 2019. So the first thing we find is that the traditional vision annotation only have a few hundred or thousand categories. So that's definitely not enough to learn this type of to do this type of task. So we start to build one of the few early visual language model, visual bird model, where influenced by the design of bird, we also hide some of the word in the captions and provide these visual embedding and as a model to predict what is missing in the caption. And using similar training mechanism like a bird model, now the model can actually learn this correlation between the cat in this image and also the word like birthday. Right, so birthday is kind of an abstract concept, but the model can learn that correlation by using this kind of max out word prediction task. And we also design some sentence image prediction tasks kind of similar to the bird to predict next sentence that you embed the sentence and the image into a certain embedding, and then you predict if this captions is correlate with this image or not. And fast forward to 2021, OpenAI released this clip model that is a very well-known model for vision language community, and a lot of work built on top of that. So they're also using some similar learning objective, but they are now doing this with a much larger scale. So they leverage a median of the image and caption data, and then build a model using a simple way. Basically, you embed each of a sentence into a sentence embedding, and then each of the image also into an image embedding. And then if this sentence is a caption of this image, and the inner product of these two embeddings should be large, otherwise it should be small. Right, so using this constructive way, then the model actually can learn to generalize to identify the different type of captions of the image. And then with some instruction fine-tuning, so now you can actually ask the model, is this image a tree in a winter snowstorm, like the picture showing here? And the model can actually recognize this kind of a new visual concept by just training this in this image and caption data. So at that time we think, okay, maybe we stop here. That this is the way we can solve the task. But then we find that, of course, the answer is no, because when you have a longer description, a more complex caption, now the model start to fail to recognize that particular object you mentioned. So we dive into what happened in there. And one thing we find that is align the vision and language at image and caption level is not enough. You need to go into a much deeper level to perform that alignment. So many people looking at this problem from the vision side to show how this image encoder is not good enough to perform this type of task. We look at this from the language side, that we find that even a very simple component for this system, that encoding the text into a factor already lose a lot of information. So what we did is we take the language encoder from this clip model, also many other type of different sentence encoder model. And then we see that once you encode this embedding into a factor, were you able to decode that information back in the sense that you can build a decoder to based on that embedding to generate a sentence and see if that sentence match the original sentence you put in. Okay, so we find that if this is a simple caption that talk about just one object, mostly the model can recover it. If this is one object with some adjective, and most of the time it can recover it, a lot of time it will miss that information. And if you make the caption more and more complex with 2 objects, 3 objects, and multiple adjectives to describe what happens, then the model mostly cannot actually recover it. So this number I'm showing here is for the case that you have two objects and then two abstracts, sorry, two objects to describing that object, and only about 30% of the time the model can recover that information. So basically, this align with what we observed from the language side, that basically, like Raymond said, it's very hard to encode the long sentence into an embedding and able to capture all the information. Okay, then what should we do for that? So aligning from the image and the captions level, we're going to lose a lot of information. So what do we think we should do is we need to go deeper and align in the level of the object in the image and the face in the text. So like noun phrase or adjective or other type of phrase. So we look at this face grounding data set in the computer vision world. So usually they don't have a lot of annotation, but they do have a very detailed annotation, like give you a caption and the image, and they annotate that what noun phrase in this caption is corresponding to the what objects. What noun phrase in the text in the caption is corresponding to what objects in the image. So for example, in this example here, you have a woman that aligned with this green box, and this blow dryer aligned to this yellow bounding box, and a protective goggle to this green box. And then we further augment this data set with a lot of different kind of prompt. For example, you can from object detection data, you can provide a list of the object you want to detect, and then also align, those objects appear in the image with the noun phrase in that prompt too. So you can use this uniform framework to describe a different type of vision task, but for all of them, they're trying to solve the same task, basically how to ground the face in the text to the image object in the image. And then we can use some similar method as a clip does. Like now you get a representation for each noun phrases here, and you got a representation of each of the object there. And then if these objects is described in this noun phrase, and they should be aligned, and their inner product should be higher. Otherwise, it should be lower. And by moving this to a more low level of granularity, now the model can do much better. And of course, you need to also do some small technical thing to make the thing work. For example, if you just align them in a high level of representation, it's not enough. You also need to add in alignment in the more lower representation layer as well. But overall, in this way, we will be able to translate a bunch of different image annotation data into this face grounding problem. So for example, you can get from the detection data, so they have a lot of annotation, but they only have a very few category. And versus you can have a go grounding data that you have a lot of unique faces that are annotated, but the data size is relatively small. And then you can further scale up this data using the distance supervision method. So basically, we can make assumption that if this phrase is appear in the caption, and most likely they will be corresponding to some object in the image, right? Because usually your caption will describing what happens in that image. And by doing so, you can actually using the weaker model to perform this face grounding task. And then with a higher threshold, lower threshold to make sure they align to some, the faces align to some object in the image. And then you can use this way to collect a lot of face grounding data and then retrain your model on top of that. So with this distance supervision method, we are able to collect about 24 million image caption data with about 78 million boxes and about 60 million of unique faces, and they become a large enough data set that you can train a pretty good model. So in that CVPR paper, we showed that using this method, you are able to recognize some novel object much better even than some supervised model. So in this in this detection in the well data set, they have a lot of novel category, like you need to recognize the hole in the road, or you need to recognize some specific type of fish. And then you can see our performance is showing in these three different color of line. So the red line is a benchmark data. So the x-axis here is amount of the training data per category we use to train the model. So 0 means 0 shot, and 1 means that you give only one image for each category. And then it's up to using the entire annotated data set we have, usually have about 100 images. And the y-axis is the performance of detecting that particular object in the image. So the red line you see is a benchmark. And the blue line is one of version of our model using a smaller encoder, and the purple line is the one that using the larger encoder. So you can see even in a 0 shot performance, this purple line is already matched that the model that trained with more than 10 image per category. And with a 1 shot of a image, then you already match the baseline that using all the data. And this is basically just kind of weakly supervised using this image capture data. But what exciting for us is that we see that the model start to have kind of a capability that it can recognize the object through the description you provide to them. For example, if I ask a model to recognize the stingray in this image, and originally the model cannot recognize that very well because stingray is not like kind of typical fish. It looks like a little bit weird. But if you give the prompt saying stingray is a kind of fish that is flat and round, and in that way, the model actually can use that description to help to detect all these fishes. And then we see that consistently in our data set that when you provide a better description, and the model can actually recognize the thing better. So again, we think we are done here. Okay.
So you use the word learn at the top. Is this actually learning anything, or is it just doing better detection by trying to identify tiny boxes that are stingrays and flat?
So in this case, we just are trying to identify the bounding box that recognize those particular object you mentioned.
Yeah, so there's nothing that tells you this is a property of stingrays in general, and you should.
No. No, this is just yeah, the description comes from human. Yeah, we actually have a recent work that we're trying to do that in the reverse way. That as a model also to generate a distinguished feature that you can use to identify the particular objects.
I was interested to see a couple slides ago, you had annotated the view as one of the objects. I think it was, sorry, maybe it's 2 forward. Oh yeah, here. In the lower right, you have the view as, but I wouldn't think of that as an object in the, so I just wonder if there's anything interesting to say about the annotation guidelines. Were you trying to do every noun phrase or?
That's a very good question. So this one is automatically annotated by the model. So you do have a noise, like the view could be a kind of a noise annotation here. Yeah, well, it's actually quite accurate, but yeah. But what we do is like basically you have all the noun phrases in the caption. So you run the simple syntactic parser. So you got all the noun phrases, and then you see if the model can align this to some of the object in the image.
Okay, yeah. So you weren't filtering. So you basically assume every noun phrase in the caption is an object in the image.
Not every, but like there's a threshold, right? So you can in this phrase you can build a threshold that lower. So in a way that most of the phrases will align to object if it has some confidence to do that.
Okay.
Yeah, but in the real world situation, that might not be true because you could actually have an object then a description of some phrases not actually appear in the object.
So, but this is for the construction of your training data, right?
Yes.
Okay, so you have a semi-automated process where you annotate and then filter based on confidence, and that's your, okay. That makes sense.
Exactly. Yeah. Yeah, and also forgot to mention that. So this is actually a good example to show that what is distance supervision work, because that if you look at this vaccine, and also this a syringe. This is kind of a word that not actually like a category appear in the notation, but because you know these are two things here, so you kind of can align that to this, and then you know there's a one box here, so you can align that to the scene. So that kind of a distance supervision can help you to annotate the thing in this way by using some contextual information. Okay, so we kind of thinking that we again kind of done here, but then we again find that there are many other problems that if the description is relatively short, then that model will reasonably well. But that model also have several other problems. I will show you in the next few slides. So one problem we see is that if I want to just give a description and ask a model to based on the description to recognize an object. For example, I say I want to recognize a kind of a tool that has a wooden handle with a round head used to plumbing or hammering. So here I refer to a mallet. And the model can actually do pretty well and then recognize that tool in the image by using that description. But if I provide you another description that is some object looks similar to a mallet, but it's actually an axe, right? So then you describe this as a kind of tool with a long handle, a sharp blade, could be used for chopping wood. And the model actually recognize these all other objects, recognize the same mallet as that description. So means that the model doesn't really have the detailed granularity in a way to distinguish two kind of confusable objects. And then what we want to do is something that I showed you earlier, that you will be able to actually to say this tool is appearing in this object using the description, and this tool is not, right? When you give you some confusable description. So then we're trying to dive into the model design to see why the grid model a lot of time over predicts this alignment, and also why it cannot really capture those description in a detailed way. So one thing we find that is that on the caption data that we used to build this alignment, most of them do not provide a good description of the novel concept, a visual concept. And that kind of reasonable, right? Because when you describe something, you usually assume people know those objects. You will not like say, today I come to JHU, I bring a box, and the box is looked at a circle, blah, 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 right? So you will not really define those objects in your conversation. And this thing is actually relatively easy to fix because you can just ask a GPT model or any model you like to provide a visual description of different type of object in different category. And most of the time, it gives you a reasonable description. And then you can further fine-tune your model on that data set. So then the model learn from those description to recognize those objects. So we use this way, we can collect about 10,000 of noun phrases using this conceptual caption and visual grounding data. And then you can fine-tune the model on those data. So what we find is more difficult to fix and more problematic is that the model don't really insensitive in a way that you read the description carefully. So a lot of time, the model just roughly look at those description, and when you capture some word or capture something, then you say, "Aha, I got it," and then just make that detection, and that causes that problem. So for example, there are a clown here who is making a balloon animal for a lady, and for the grid model again, it can recognize like clown well when you provide that description. But if you change the description to a clown like kicking a soccer ball with a lady, and again, the model make mistake by recognize that person who is not actually kicking a soccer. So we call this kind of a shortcut because the model just see the word clown and they say, oh, there it is. And then so that must be the one I refer to without really looking over those description and all these specification. Okay, so the way we solve that is that, again, we provide description fine-tuning data by asking the model to generate some confusable situation and by switching those description. And here we remove all these specific noun phrase by using the high-level category to describe the object. So for example, we use the tool instead of a mallet or X, right? And then because this is a same word tool that used to describe this wooden handle, blah, 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 the mallet, and also use the same word tool, with a description of X, the model now needs to distinguish these two tools are different. And then in that way, the model will actually look all these phrases after that word in order to see that this should be aligned or not.
So I just want to make sure I understand this. At the left of the slide, Glib was originally trained asking to identify nouns.
Yes.
And in some cases, the answer is not in the image. And that's why cat is in a different color.
Right.
Because there's no cat in the image and it has to recognize that. And you're basically just going from nouns to compositional noun phrases.
Yes. Yeah.
That's the difference.
Right. Right. Exactly. Yeah. Yeah, and then you can do this with a compound noun like polar bear. You can do it with like the noun with the following the clause to describing the noun and this and that. Yeah, and then you can basically generate a lot of these different data set. And then now the model will need to learn to use all these specific description to detect the objects.
And the confusable phrase is not determined using the vision system at all, right? It's something which is maybe it's generated by an LLM. Do you ask the LLM to come up with something that might be visually confusable?
Yes, yes. So exactly. So we actually ask the LLM to give you something that visually confusable, and then in some cases we also try that give the image, yeah, and then let the model to tell me that some object looks similar to that image.
Okay, so things that are wrong but are still
Right.
still have reasonable probability.
Exactly.
Okay.
I have two questions. So one is how to make sure that description generated by GPT is actually correct. So if, like, say, for example, in this case, kind of two would handle with the round, blah, blah, blah. Does it have to, I don't think it has to, like, have the robber. Still the same function.
That's a good question. So first we give the image to ask the model to generate a description of that particular objects. Right, so in that case, I think wooden is come from it recognized there's a wooden handle. Yeah, yeah. But also related to the question, we do some human annotation to make sure that the generation has a high quality. Yeah, I think it's kind of 95% of the time it is right, but sometimes they have some noise. Yeah, and then yeah, and then we fine tune the model on that data set. So there are some noises there, but that's good enough to let the model to learn that. Yeah, yeah, of course. Yeah, yeah. Mhm.
Vision, right? What is the visual concept? So it's like something already like a concept of like object part.
Mhm.
And because object part like how many shares about different kind of objects, so that's something you can propose. Like,
Yeah.
and then make it easier.
Yeah, that's a good question. Yeah, yeah. So for this particular word, we only looking at the novel objects. Yeah, so we just learn aligning a noun phrase with the object in the image. Yeah, but more recent what we are doing, we also looking at the part of the objects. Yeah, so that can go into even more detailed level. And then we also looking at the adjective and the verb like related to the object too. So trying to learn the affordance and other information about the object. Yeah. Yeah. Okay. Yeah, and then just quickly show the performance of that model. Yeah, so this Army label share task in the CPPR workshop. So basically it gives you some image and then you need to recognize the object, but also you give some specification, like not just recognize all the donuts, but I want to get all these chocolate donut, for example. So then the model need to go beyond to use those distinguish description in order to recognize exactly the right the object that you referred to. And all the system performed very badly in that test. So we show that with this model that you fine-tune the model to do the description instruction fine-tuning, you can improve significantly with any of these visual detection model by 4 to 5% in the average precision, but it's still far away from satisfactory that you can really use. Yeah, so there's still a long way to go, but that's showing some significant improvement. So we also have a demo. So if you're interested in that, you can play that in a Hugging Face. And I just make a fun demo cases that this is the student who performed doing this work. So when he graduated, we have a picture there. So I give that picture into the system. So you can see that the model can actually recognize that particular students, not because he looks younger, but also we say the student holding a flower. So you use that description to recognize that the person on the left-hand side is a student. And another interesting thing, you actually recognize this is a PhD defense. So I guess most of PhD defense has a slice now. Yeah. Okay, so now I want to switch a little bit to talk about the other line of a project that we want to teach the model to learn from the rule and the constraints. So this was kind of come from the line of direction I did during my PhD. So I kind of excited to see how this can be working in this LLM times. So basically, we know like human decision often governed by many rules and guidelines, right? And then in applying LLM to the real application, we may also face many different situations that require the model to follow certain rules. So for example, you need to, in some cases, you need to follow certain particular format like JSON format or YAML format, right? And then in some other cases, you want your generation follows some particular style that you need to be formal when you do the translation. And then sometimes you need to have some safety, make sure your generation doesn't contain some toxic output, and you need to make sure you pass on toxicity classifier. And also like in a creative setting that you want to the model generate, for example, a poem that with certain rhythm. So we've been looking at the problem to ask like, can an AI model to be designed in a way that it can adhere to the rule you provide to the model, and you can learn to follow them effectively. So first of all, we try that if you can just simply prompt the model to follow those rules. And we try it in a very simple setting that we just ask the model to follow some lexical constraints. So for example, you ask a model to say, I give you this set of the description of the person, and then generate a profiling paragraph that contain all these features of the client. Okay, and then supposedly the model should generate the output that using all the word in this input constraint, but a lot of time the model cannot do that. And then we also try a different type of setting, like as a model to generate story based on the character you provide, generate a poetry, recipe, and this and that. And then we try to benchmark if a model can really follow those lexical constraints in that generation. So just show one example here. So this is a data set called Common Gen annotated by AI2. So the task is I give you a set of words and you need to generate a sentence that follow the common sense that contain all these words. And our goal is trying to make sure that when the model generates that sentence, it really contains those words that you provide. So what do we find is that if you give you a very few concepts, like 3 or 4 concepts, and the modern model like GPT-4 can actually perform pretty well, like showing in this blue line. So almost like 100% of the time, it can give you the sentence that follow the common sense and contain those words.
Right, how is success judged?
Sorry?
How is success judged? That's the vertical axis.
Yeah, so this was judged automatically by another GPT-4 model. Yeah, and but that one also verified by human annotation that is reasonable. Yeah, but here I'm more interested in just looking at the successful rate in terms of that it really contain those words. Yeah. And then we find that when the number of concepts increase, like when you ask a model to generate sentence content 10 or 15 words, and the model start to fall apart, and you start to even the GPT-4 model, like in this blue line, cannot 100% do that generation. And it is basically the same for other application that we try. For example, generate a recipe given the ingredient, table to text based on the entries, and a profile writing as I showed you earlier. And when you only have a few concepts, the model can do it perfectly. But when you increase the number of concepts, then it start to unable to do that. So we do a bunch of analysis in the paper. So for example, we see that a lot of compound word was broken into several pieces. So that's why it's wrong. And another interesting thing, we find that if you give a list of objects, list of word, the model usually can handle the first few words very well. But at some point, you will start to unable to continue the sentence with those particular words. So you can kind of changing the prompt method, like doing in that paper we showing that you can do define and counter, so make the problem easier. But today I want to talk about a more fundamental way to solve that. That is that can we let the LLM to do the inference with constraint or even embed those learning signal into the training time. So in one of the newest paper we published 2 years ago, that we're trying to resolve this challenge that can we provide some controlling criteria in the sentence level that all these constraints need to be satisfied when you finish the sentence. And then consider the output is generate auto-regressively, that you generate the next word, right? Not using some other method to decode the sentence. And then because the LLM is pretty large and also it's not factorable like a traditional HNN model, then we're trying to see how we can solve the problem in that kind of setting. Okay, just provide some little bit mathematical description of the problem. So we assume that you want to build a model in the way you generate this distribution piece data. So in this case, this piece data can be considered as a large language model, and it can factorize into given the previous context you predict the next word, which I represent this as a yi. And here I define a constraint kind of pretty general that it can be anything. So it's basically just a function, give an input and output, and you return to me that if that constraint is satisfactory or not. And in real cases, you can actually define the constraint in a more description, provide, you can use a different way to describe the constraint. And here I just provide a very general description. You can define that too, yeah. Yeah, and you can also use it like first order logic or other way to define a constraint. But if it is a more, fine grained, and then you can actually break down it more easily. But here I just talk about the general case. Okay, and then our goal here is basically say that I want to build a model in a way that will represent the distribution Q. Such that if the constraint is not satisfied, then you should not put any probability on that distribution, right? And at the same time, you want that distribution of the Q is somehow similar to the original model's distribution piece data, and you can characterize that using the KL divergence, right? And then finally, if I want to do auto-regressive generation, then this Q distribution I design at the end of the day should be able to factorize to just predict the next word. Oh, that's a good question. So you can, here I define it as binary, but you can relax that to a soft constraint. Yes, you can also say that in expectation that need to higher or lower than certain threshold. Yeah, in expectation, yeah. Okay, so this is kind of the problem that people back to 15 years ago have been thinking about. You can use posterior regularization to train and also to inference the model. But at that time, that thinking about the large language model, right? So if you write down what I want to do is basically you want to minimize in the KL divergence between these distribution I want to build with the current model P theta in a way that the constraint is satisfactory. And if this is talking about just one token at a time, or if this is factorizable, then basically what you want to do at the end of the day is you can build this closed form solution that if this constraint is not satisfied, then the distribution should be zero. I mean, the probability should be zero. And then you move all these probability mass to all the other output that satisfy that distribution, right? So then back to the question that how I can identify that kind of alpha to do this normalization. So again, if this is a traditional model like HNN, and we know how to do that, you can use a forward-backward algorithm, and then you can learn this marginal probability, and then you can basically do this perfectly. But then again, the challenge here is that we are talking about LLM, not just a HNN model. So then the question is that for the LLM, can we do something similar, right? Can we also factorize that constraint into a token level? So we find that we can actually build another model to do this approximation. So specifically, you can have a base model to sample and then to generate a lot of example. And then for each of the position, you can predict how likely the constraint will be satisfied if you continue the generation. And you can collect the training data to do so. And then we find that this auxiliary model cannot do it perfectly, but in some degree, it can predict that if the constraint will be satisfied at the end of the day when you predict this as a next word. And let me skip some of the detail, but basically you can build a model like that, and then you can actually use that function to provide this estimation, and you plug in to that function I mentioned earlier, and this can actually make the magic and then and give you a good prediction. So we are not the first thinking about this kind of idea. There are several related work like huge model was also doing something similar, but they didn't train the model in distribution data. So we find that at the end of the day, likely to deviate from the model's original generation. And we find that it is actually very important that using the model to generate the data that you use to train this auxiliary model. And there are a bunch of detail that is in the paper, so I'm going to skip here. But basically, in the experiment, we showed that you can use this way to guide the model to generate an output that can pack the toxicity classifier. So for example, you pick this perspective API, which can tell you that this sentence is toxic or not, and you set a threshold based on the score they return. Then you can actually train the model. You can actually use this as a way to guide the model to generate a sentence that unlikely to be detected as a toxic. In the same time, mostly keep the perplexity of the model's performance. Okay, so this is about how we can use an inference method to guide the model with constraint. And what if we can learn this with constraint? So the same method can be applied in the learning too. And then we actually consider this in a very interesting setting, that if you want the model to avoid generate the toxic data, a lot of people were thinking that I can just remove all the toxic data in the input, right? And then the model will never see what is a toxic, so it will not generate that. But turns out that might not be a good solution, right? Because then the model would be blind to the toxic, right? And then you ask the model, this is a toxic center or not? You say, I don't know, right? So you kind of got this dilemma that you need to let the model see what is toxic content, but also you don't want the model to generate that. So we use this method to actually train the model on top of this toxicity data set. So you see a lot of the toxic input, but also at the same time, you put a rule that you should not do that generation. Okay, then a similar method works. So you can basically use in the same way to find this Q distribution I was describing. In terms of a training, and you want to that the model to move toward this feasible region, in the sense that you're trying to minimize the tail distance between the current model and what we consider as a best model at that point, right? So then you can basically doing this iteratively. Yeah, I kind of again skip a bunch of the detail, but you can basically use this as a regularizer, and then you can that the model to move more and more toward this feasible region we define, while trying to again still training with a language model loads on that data set. And there are more technical detail, for example, that you can actually build this as a pipeline, but that would be super slow. And you can actually using some delay update schema that when you trying to build an auxiliary model, you are not building the current data set based on the current auxiliary model, but based on the previous one, so that you can actually make this as a kind of a pipeline. And in that way, the model we find that the performance will be similar, but it will be much, much faster. Yeah, so there are a bunch of a technical thing. Again, we discussed in the paper. I'm going to skip here. But in terms of performance, it's quite interesting. So this is the base model. And then the red line you see here is an evaluation on the MLU data to show their general utility. And the blue line is the performance on this toxicity generate data set. So higher is worse because it means that you generate more toxic output. So you can see that if you just filtering the output, then it doesn't really work. So the toxicity is still pretty high. And then you can do something like IO method. But the IO method, the problem is that you will lose a lot of performance. And then you can also just do that in the inference time, but then in that case, the utility will drop a lot because the model was got confused. And this training method actually give you a kind of balance between the two. Okay, so that's kind of our work on how to teach the machine using the rule. And at the end of this talk, I want to just spend 5 minutes to talk about a little bit more about my collaboration with others on this direction. So I think nowadays the large language model is kind of like a stage. We have an airplane in 1914, and the image showing here is kind of a first commercial flight that flying through the strait. And if we want to get the NLP model into the situation we have now, like we have airplane today, then we still have a lot of things to do. We need to have a model, have people to trust the model. So you really use that, and we need to ensure the safety and many other components beside the performance. So I was interested to see how we can collaborate with people outside the CS when using this model, and then how to see they kind of able to trust those models when they perform the test they are interested in. So I work with people in the public health, sociology, and psychology on how to understand why people commit suicide. So there is a NVDRS data, the National Violent Death Reporting System, that when people commit suicide or there is a homicide, there will be social worker write down what happens in that data set. So we use a model to analyze that. And then we want to see first, if the social worker have some internal bias when they're writing those documents, and also why the people commit suicide, what is the main cause, and this and that. So one of the interesting things there is that we find that the current model is performed badly when there is LGBT cases. So the model kind of usually assume, some male's wife is always female and this and that. So that causes a lot of error. And then again, we want to make sure the model can be worked on every cases, especially for LGBT cases in that data set, because LGBT individual has a 5 times more likely to commit suicide than usual people, right? So then we want to really see what happens. So we have a bunch of research on that line lead by Elia. Yeah, and if you're interested, I would like to talk more after the talk. And the other interesting thing that we are doing is we want to do epidemic forecasting. So that comes similar to Mark-Jesse's work earlier. That basically we look at social media and then trying to see that when there's a pandemic happens, how people talk about what happens, and then can we use those signals to see there is a pandemic going on nowadays. So the challenge there is that the normal event extraction model doesn't have those annotation of a pandemic related annotation. So we work with a public health professor to identify what would be the important events that they think when they use to do the epidemic prediction. So we build a general model that the model can follow certain temporary profile with a description, and then use that to do the event extraction. And because this model is relatively general, so the public health expert could directly use language to guide the model to identify the event they are interested in. We also apply our constraint translation method. So we can translate the data we annotate into 65 language across different countries. So in that way, with a constraint translation, we ensure that those labels can be translated into different language. And then this will much better than the usual way people build the multilingual data. That is just first translate the data and then do the annotation again. So this is some kind of a quick result that we get from trying to predict the pandemic happening for COVID and for the monkeypox. And you can see that the red line is our method. So you can see some peak that even much before those warning from CBT and others. Okay, so in the end of talk, I just want to quickly acknowledge all the funding, current and previous funding, and also my group members. Yeah, so I just put the conclusion here that trust is very important to that people start to using those systems we build. And my research is focused on how to use language and rule to guide the large language model that can earn trust from human. Okay, thanks for your attention, and I can answer any question you have.
All right, so great. First of all, that was great. So now I'm going to ask hard questions.
Okay.
So you talked about vision and language, and you talk about going beyond the traditional boundaries. So what about speech? So what kind of things do you think are possible when combining speech and speech processing models might do with the types of language feedback that you're giving the system?
Yeah, that's a very, very good question. I didn't touch upon speech mostly because I already touched upon programming language and language, multilingual and vision. But I do think speech has a lot of interesting information that can be used. For example, the emotion is mostly showing in speech. And also I was interested in, yeah, maybe it's more like Felix things. Like you want to do the language translation for those language that don't really have a written format, right? So that kind of information that you can only get from the speech signal. Yeah, and I know a lot of effort in the community now trying to build what they call any-to-any model that can better incorporate all different modality that into just one single model. And I think some of the thing we developed here could be quite related. Yeah, and then we also kind of move into work on those any-to-any model too. Yeah, with some of limit compute we have. Yeah, but yeah, definitely I think that would be a good direction to go in the long run.
Okay, let me say something else briefly. So I'm thinking of like, so one of the things that I've been really impressed with is OpenAI's whatever the advanced speech stuff, where you can give language feedback that then changes the voice. So you could say, this should, what I like doing is say this with a French accent, and then I'll say it, and I say now even more of a French accent. It becomes even more right. And so I think like there's a lot of tasks in language, like you're talking about like object recognition here. You can imagine in speech, you're trying to do like speaker recognition or diarization, or, you know, there's a range of things, and you might want to give the model some hints, right? Like, so you
Right.
might say, well, I want you to do diarization of this conversation. There's 3 people, and these are their names and basic descriptions, and that might help the model, you know, figure out who's saying what. But speech is really different than vision.
Right.
And so I don't know if this is like, yeah, all this kind of stuff could work there, or there's some unique challenges where we're not ready for it, or maybe you have no idea.
No, I mean, I think the speech is similar to the language in the sense that it is only have one direction versus vision data has a 2-dimension or 3-dimension, even more if you consider video. Yeah, and but on the other side, that speech involve those you know, not just a discrete token, but also the wave and all other things that I think it's more from the signal processing that you need to capture those information that might not be easy from my language perspective. Yeah, yeah, and yeah, I mean the current way people thinking about that is you also get the basically convert the speech into different kind of a speech token. Yeah, and then do the all the learning on top of that. One question I'm not sure is that when you do this encoding step, they may already lose a bunch of information like I show in the vision language cases too. Yeah, so that's something I think would be a very interesting research direction to see that how much deeper of this alignment we need into which granularity. Yeah.
Thank you.
Yeah.
Control systems are very always think about these things. We even instead of then using math, then you need equations, then RL and organization. But here you show that we're trying to use natural language, which is very interesting because there are many possibilities. It's very hard to use math, and now use language. But also, do you see what's the connections there? And then is there a way? Maybe in the future we can just use natural language,
right?
Give feedback and give strings and give rules.
Yeah, I think that's very interesting question. So we started looking at kind of a physical alignment between vision language. And then one of the problems exactly what you are saying is that can we let the model to understand the equation? So because we actually have pretty good science and math model, that the model kind of learning what is math there, right? Then can we do something like humans, right? Like to understand the physics work through the equation and then apply that into a certain application. Yeah, so one particular thing that we're trying to do is that consider the text to video model. Can you make sure the model generate the video that follows some physics rule, right? The law of physics, Newton's second law of physics, this and that. Yeah, and we find that it's quite difficult actually. Yeah, one way is that now a little bit not sure the model really understand the equation. That's one thing. And then second is that even you have that, how can you get the model to learn from that equation? So the current step we're doing is through the simulation system, but I think you would probably need better system to do that. Yeah, yeah. But definitely, I think it's kind of the next 1 million question, like how the model can really understand math equation and like human, right? And then use that to do reasoning and this and that. Yeah.
Anyone else? Okay, let's thank our speaker.
Thank you.
Looking for people like her and she seemed interested. She didn't come here asking questions. Just yesterday, she wrote me saying, hey, so you guys didn't mention that. And she was a big professor now. I'm feeling she might be coming up with a solution. Together with somebody from Europe technology or Europe things. Right.
Enjoy lunch. I'll see you after lunch.
Okay. Somebody in Europe, okay, they have a center for clinical applications. So she may want to talk to somebody. I was thinking of referring her to you, but if there's someone better.
Let's see what she does.
And also,
What
Andrea-
department is she in right now?
I think she is the biomedical engineer.
Uh,
Her primary is biomedical. If it's not there, I can find you where it is, but I'm.
No, you're right. She's in bio, I'm good, but she also is in EC. I mean, she has appointments at EP and chest. She can go anywhere.
That's what I said, primary is. And then she's in EC and she's in some clinical department as well.
So.
Technically, she's very solid and she seemed to have a pretty good idea about where she wants to apply these techniques. She has good clinical confidence. So she understands the clinical side, but she didn't come across as one of these people.
So I can look more carefully, but I would say, I don't know who's doing devices. Okay, so definitely people at Hopkins doing devices. But all the people I know, they're in the medical school. I don't know who on this campus system here.
And the other question was like, she probably wanted to talk to somebody first, even because she's not like looking for a job. So I wanted to put somebody good in front of her so that she could speak.
Yeah, I can talk to her.
Yeah.
Although if you want to find someone who's more in her area, we can do that.
I mean, I've talked to her already and I've told her generally both about the overall AI scene and I've told her about things like the Malone Center and
Yeah.
other activities like that, how CLSP is involved in it, but it's not mainstream to us at the moment. Although it's not because it is. Yeah, okay. So
Okay, so if she goes, the problem is when she goes to DMV, I mean, they're always hiring, but they're not hiring as part of the DSAI.
Yeah.
So.
I think we want her as DSA. I think she should.
Right, but it is possible to do a joint hire with DME, I think the DSA, like if DME and ECE jointly hire her, then she could count as DSA. Yeah, that is not an option. It is actually better to get her before a full professor because the bar is really high for full professors. And so I would like, I just like that this has been I don't know if it's a problem, it's just a reality.
Is there a PDP cluster in this area? I know they haven't announced them, but I think they will decide.
Yeah, and you wanna know what they are?
Rama mentions. He said something to the effect that
These are what they are.
it's,
I know that they're not easy to read. The last one isn't decided. It might be decided. This is a follow the whole. So there are like maybe this one. That's the one I would suggest. Yeah, and it's person Kathy McDonald. I know Kathy. I know this person. I don't know what's in here. Carrie Business School. Carrie Business School. Kathy, I thought was awesome. Who knows? It might be a new